Hello everyone, welcome to another in a series of short videos that we're creating here to try to explain the idea of climate controls. If you've been following these video tutorials in order, then you will already have heard the latitude tutorial and the large bodies of land and water tutorial. Today what we're dealing with, the third one now, is elevation. All three of these climate controls are temperature controllers. We found that latitude has a direct impact on temperature. The higher you go in latitude, the colder it gets. Large bodies of land and water have a bit more of an opaque effect on temperature. It creates a scenario where temperatures are either more extreme or less extreme depending on whether you live near a large body of land and water. With elevation, what we're going to find is we get back to a situation where there's a direct connection between what your elevation is and what the temperature is, either hotter or colder. So let's get on with the show here, and we'll get into the nitty-gritty details here. Concept organizers are now something that you should be familiar with in terms of filling them in with notes, and the last slide of today's presentation will show you what a finished piece should look like. So again, today we're dealing with elevation. This is now the third climate control that we've talked about that affects temperature. And there's really a couple of ways that you can go about explaining this that both kind of say the same thing. As elevation increases, the temperature of a place will decrease. A more simpler way to put that would be the higher up you go, the colder it gets. And the thing to keep in mind about elevation is that the inverse of this rule is also true, in that you could switch around these two words and this trend would still be true. So if elevation decreases, goes down, temperature will increase. So it's sort of like a teeter-totter effect. As one goes up, the other goes down, or vice versa. So the how and why this happens mostly has to do with the amount of particles that are in the atmosphere and the change in the density of those particles as you get higher in elevation. So the way that we've tried to explain this, to simplify this situation, is that as you go up in elevation, the air is going to get, quote, thinner. And what that means is there's fewer and fewer particles, or there's less density of particles in it. And when we say particles, we're meaning mostly water vapor, dust, carbon dioxide, things like that, okay? And what this sort of has to do with temperature control it comes down to this. The sun's rays, as they're coming in through the atmosphere, if they come into contact with any of these particles, then they're going to be absorbed by those particles and re-radiated back out. And that absorption and re-radiation is what we feel as heat. And so if there are more particles in the air, there's more particles for the sun's rays to hit and to heat. And so you feel warmer at a lower elevation where the air is thicker with those particles. The way we've written it here in our notes is with less matter or less particles in the air, there are fewer for the sun's rays to hit and to heat as you go higher in elevation. And so that sort of in a very rudimentary, this is a very simplistic way to explain it, but it is colder the higher you go because there are less particles in the air for the sun's rays to hit and to heat. Now, the diagram itself that we found, does a nice job of showing you, that as you go up in elevation, the temperature of a place goes down. What we're going to talk about shortly in the other notes section of your notes organizer is that there's a very precise rate at which temperature changes because of elevation changes. And so those notes are coming in a minute, but I just want to point them out here now while we can visually. You're starting off, it's 27 degrees and you're at sea level, and as you go 1,000 meters up, the temperature has dropped just over 6 degrees, and it continues to drop every 1,000 meters by just over 6 degrees. So that trend we're going to talk about and give it a name in a minute, but let's change the diagram to the one that I would like you to make on your actual sheet. And what we've done here is we've actually created two separate diagrams. There's an upper and a lower, and they are divided by this dotted dashed line here. So the top one, really what it's designed to do is just show visually that there are far more particles or denser concentrations of particles near the ground level. Okay, lots of dust and other particles, and that's going to mean there's more heat near ground level because there's more particles for the sun's rays to hit and to heat. As you go higher and higher up in elevation, there are less particles the higher you go, therefore less particles to heat, which equals colder temperatures. The bottom of this box is designed to show a rudimentary replica of the diagram that we were just looking at previously. And it starts at 0 meters and 20 degrees, and here we're going up by a very precise amount. I think my math is a little off at the very peak of this mountain, but for every 1,000 meters, what you're noticing here is that the temperature is going down by 6.4 degrees per 1,000 meters. And now it's time to make this, well, let's skip the examples quickly here, and we'll go over to the other information box, which really does sort of give a name to this precision of temperature change. And so it's called the environmental lapse rate, and this is the rate at which temperature changes with elevation changes, and the rate is very precise. It's been measured as 6.4 degrees per 1,000 meters of elevation change. And remember, this doesn't work just one way. As you go up in elevation, the temperature will go down by that amount, but it will also work in the reverse. So as you go down a mountain by 1,000 meters, you will be going up in temperature by 6.4 degrees. Sorry for the zipping around here, but I just want to point out that this sort of, if you were to climb this mountain, it would be getting cooler, but on the way back down, you would be feeling more and more warmth as you get further down in elevation. And that's really the key, is that this climate control will work both ways. So the examples that we've given you here are places that are high in elevation, like Banff or Denver, are both going to be cooler places because of the elevation that they are at. Winnipeg doesn't have a particularly high elevation, and elevation is not something that really affects Winnipeg for that reason. Okay, elevation works best as a relative measure. So you'd be able to say that, for example, Banff is cooler at its elevation than another city at the same latitude would be at a lower elevation. So unless you get into very extreme elevations, like over 1 kilometer in height, the change in temperature is not so drastic that you're going to be able to feel it very often or easily. Okay. So the other way that you can see this climate control in real life is the fact that on mountaintops you will see snow, where at the bottom of the mountain there's no snow, and that sort of is a visual demonstration of how the temperature is gone below 0 as you've gone further and further high in elevation. But as you go down in elevation, temperature warms up enough, and at some point snow will melt and turn to liquid water, and that's why you don't see snow at the bottom here of these pictures. So I think that pretty much takes care of it. The other information we've already looked at quickly, and so I'm just going to flip to the final page, and what I'll try to do, I don't think I'm going to be able to fit all of it on, but I will see what I can do. We'll just get it in there and bring it up. And you're not going to be able to see all of the notes this way, but you've got most of them here as a close-up. And you can also, peel this video back a bit and just see the whole page there on the side. And hopefully that takes care of things, and we'll see you on the next video.